All right, cool. And we're recording. So let's do this. So problem 1, solve triangle ABC given all three side lengths, A, B, and C. So since this is a side triangle, we're going to want to use the law of cosines to start by solving for this thing. And the hint that I've given in some of the past lecture videos is that if we have all three sides, meaning we have our choice of any angle to start by solving for, always start by solving for the biggest angle. Because if there is an obtuse angle, that being an angle more than 180 degrees, then the law of cosines should pick that up because cosine inverse is defined in the second quadrant. Whereas the law of sines does not find an obtuse angle because the law of sines is always stuck in the first quadrant. So since side C is the biggest side, that means that angle C is the biggest angle. So I'm going to start by trying to solve for that. So I'll look for 7.3 squared being equal to 3.1 squared plus 5.2 squared minus 2 times 3.1 times 5.2 times the cosine of angle C. Which means that C is going to be equal to the cosine inverse of 3.1 squared plus 5.2 squared minus 7.3 squared all over 2 times 3.1 times 5.2. And we'll pop all of that into a calculator. Okay, arc cosine of 3.1 squared plus 5.2 squared minus 7.3 squared all over 2 times 3.1 times 5.2. And in degrees, I get that C is equal to 121.1 degrees. Yes, I am following a formula, and that formula is the law of cosines. C squared is equal to A squared plus B squared minus 2AB cosine C. And that's off of worksheet 14. Right. Next, I suppose we'll use the law of sines in order to find the next angle. So I'll solve for angle A, I suppose. I'll have that the sine of A divided by 3.1 is equal to the sine of 121.1 divided by 7.3. Yes, this recording will be posted later. And looks like I need to shrink this down a little. So A is going to be equal to the inverse sine of 3.1 over 7.3 times the sine of 121.1. And we'll pop that into a calculator as well. Arc sine 3.1 over 7.3 times the sine of 121.1 degrees. 21.3 degrees. And then finally, we'll need to get angle B. But we already have the other two, so this one's not bad. Just take the difference between 180 and the other two angles. So 180 minus 121.1 minus 21.3. And we'll get a number there. This is 37.6 degrees. Okay, and then we're going to get the area of that triangle. And we'll use the formula that we got off of worksheet 14, which is this one right here. Area of a triangle is that square root of s times s minus a times s minus b times s minus c, where s is a plus b plus c. So we'll start by solving for s. So a plus b plus c over 2. I want 3.1 plus, what was that, 5.2? Yeah. Plus 7.3 all over 2. That one was A. This one is B. That one is C. And if we do all of that, that is, what, 15.6 over 2? Yeah, so 7.8. That seems about right. Yeah. So then that area will be the square root of 7.8 multiplied by 3 other pieces. I need 7.8 minus 3.1, which is 4.7. Then subtract 5.2. I get 2.6. Subtract 7.3 to get 0.5. And then throw all that into a calculator. QRT. 7.8 times 4.7 times 2.6 times 0.5. And I got 6.9. Did we have units on this thing? We did. So square feet. Since this should also be in feet right there. Okay, on to problem 2. Solve the triangle or triangles ABC given the information below. This thing here, we know two sides and an angle, uh, but we don't know the angle that's in between those two sides, meaning that this is not going to be a side angle side problem like where we would use the law of cosines, but instead one where we're going to need to use the law of sines. And I know that I'm going to need to use the law of sines because my given information is that I have both side A and angle A. So that's my indication that I should be using the law of sines. I have a letter that repeats itself, so I can get one entire ratio in the law of sines. But that also means that I probably have a second triangle in this problem. So we're going to need to end up solving for both, which is, well, that is what it is, I guess. So I'll start by setting up what we know. Sine of C divided by 12.8 is equal to the sine of 58 degrees divided by 11.4, meaning that sine of C is equal to 12.8 over 11.4 times the sine of 58 degrees. So that's the last spot that I know for sure what my answer is. Once I get to this spot, because angle C right now could be either in the first or the second quadrant. So it could be an acute or an obtuse angle, and I could still plug something in and solve this equation. So we're going to have to check two different angles for C. First one that we'll call C1 is just the inverse sine of that whole mess, 12.8 over 11.4 times the sine of 58 degrees. And we can get a number here. All right. Question in the chat: how do you know when to check for a second triangle. So the way to know that you have to check for a second triangle is if the law of sines, let me back up. So you have to check for a second triangle if the first thing that you do is use an inverse sine to find an angle. Right? So in fact, we could almost simplify that to any time you have to use the law of sines to get an angle, you have to check for a second triangle. The times when you don't have to check for a second triangle is when you're only using this law of sines to find sides, because we don't have to bother with taking the inverse sine of some number. Or anytime you use the law of cosines, then there's only going to be one triangle. So if you have the law of cosines, you don't have to bother. And if you're only using the law of sines to look for sides, you don't have to bother. But in this one case where you have to use the law of sines to get an angle, then you have to check for a second triangle. Because that law of sines, because sine inverse is not defined in the second quadrant, there could be something that's missing. So, all that out of the way, one last thing that I could say about having to solve for a second triangle. I did highlight the important bit up here at the top. So if I have two sides and a letter is repeated, like I have in this case up here at the top, I have side A and side C, and the letter A is repeated, side A and angle A, that means I have to check for a second triangle. If I have two sides and all three letters are different, so I have like A, B, and C, then I go to the law of cosines instead, and I don't have to check for a second triangle. Since cosine inverse is defined in the second quadrant, it'll always give me that other angle, that angle that's in the second quadrant. Don't have to worry about checking for two. All right, arc sine of, let's just borrow this one. What do we have? 12.8 divided by 11.4 times the sine of, not 121, but instead 58. Okay, so I get 72.2. Yeah, that is correct. The final is not droppable. Also, it's cumulative. Yay. But before we get too far, let's talk about just solving for that second triangle right away. So if we are solving for a second triangle, I'd know right away what to solve for, and I have to go back to the very first angle that I get and look for a different first angle, because none of that given information will change. So angle C2 for that second triangle is just going to be the supplement of C1. So I want 180 degrees minus 72.8. And we get, what is that? 107.2 degrees. And so that angle will be the start of our second triangle. But first, We'll just go ahead and solve out the rest of this triangle, the rest of the first triangle. Might as well get B1 next. Angle B1. Let's do it in blue. Yeah. B1 should be 180 minus 58 minus 72.8. And what does that work out to? 80, 130.8. So is that 49.2? Yeah. And then we'll solve for side B1. So B1 over the sine of 49.2 is equal to 11.4 over the sine of 58, because I'll just come back up to that given information. So I'll plug in letter A. So B1 then is 11.4 times the sine of one angle divided by the sine of 58 degrees. And that angle should be 49.2. Plug all of that into a calculator. 11.4 sine, oops. 49.2 degrees over 58 degrees. I got 10.2. And we're in meters. $72.8 degrees. Okay, so there's our first triangle. Then we'll come back up and get the second one, and we'll solve for it much the same way that we solved for the first one. I'll get B2 next. It's now 180 minus 58 degrees. But this time I subtract C2, which is 107.2, instead of that 72.8 that we did last time. And we should find a number here. Let's see, so that's 165. So 14.8. And then B1 should be equal to 11.4 times the sine of one angle divided by the sine of 58 degrees. But this time I'll plug in 14.8 degrees. Since all the calculations in this side should be based on all of the two angles. And I accidentally called that B1 when I should have called it B2. Yep, and Carolyn caught it in the chat. Yep, just a bit of a mental typo. What angle did we say here? 14.8. I got 3.4. That'll be in meters. So then I'll come into this answer box and write all that stuff in. C2 was 107.2 degrees. B2 is 14.8 degrees. Side B2, 3.4 meters. Okay. So we've got Coast Guard Station Brave is 47 kilometers due north of Coast Guard Station Courage. Airplane is forced to make an emergency landing and is sighted by the two Coast Guard stations. Airplane from Brave is northwest, and the airplane from Courage is also northwest. So how far is the downed airplane from Station Courage? So we also want to draw a fully labeled diagram. So let's do this. So everything's going to go to the northwest. So I'm going to start by drawing my two stations in this way. So we have that Brave is north of Courage. So I'll put a B here and a C there for Brave and Courage. And then there's an airplane, and that'll be A. Convenient how that works out. It's almost like someone planned it that way. Right. So let's start putting some angles on here. So the bearing from Brave, which is going to be point B, is 57.4 degrees west of north. So I need to go 57.4 degrees to the west. And 90 minus, let's just call it 58, will be 32. Your diagrams don't have to be nearly this accurate, but mine can be, so I'll do it this way. Then from Station Courage, we have to go 32 degrees to the west. So 90 minus 32 is going to be 58. Also funny how that worked out. So I'm going to put my ruler down here at Station C and draw it up there. Okay, And so now that I've drawn those two bearings in, the point where they intersect must be where that airplane is. So that point right up there, that'll be our airplane, point A. So we'll also put some other things in here, like that line here, because we need to label our bearings. This angle right here was the bearing from Brave, so it's 57.4 degrees. This angle down here is our bearing from Courage, so 32.1 degrees. Oops. 32.1 degrees. There we are. And what is it that we're asking for? How far is the airplane from Courage? Which means I'm looking for this side, B. The last piece of given information, 47 kilometers due north. So 47 kilometers. That part goes in right there. So we'll start by solving the rest of our triangle. I'll get this interior angle first. So the area that's on the interior, angle that's on the interior of my triangle should be the supplement to 57.4 degrees. So this is 122.6 degrees. Since if I add that with 57.4, I get 180. I'll also need angle A up here. So we'll start by getting that one. A is equal to 180 minus 32.1 minus 122.6. And what does that come out to? 25.3 degrees. So we'll label that angle up there as well. And finally, let's actually solve for side B. So that's the thing that we were interested in. So I should have that B divided by the sine of 122.6 degrees is equal to 47 over the sine of the angle opposite 47, which is angle A. So 25.3 degrees. Meaning that B is 47 times the sine of one angle divided by the sine of another angle, 122.6 over 25.3. And we'll get something out of that when we plug it in to a calculator. 47 goes there, 122.6 degrees, 25.3 degrees, 92.7. and we'll call those kilometers. Let's make sure I didn't. Nope. All right. So problem 4. Find just the area of triangle ABC as given. And this one's not too bad. So from the Law of Sines worksheet, which is worksheet 13, we have that area is equal to 1/2 of CA sine B, or AB sine C, or BC sine A, but we'll use the one that works out for us since we happen to have exactly this information. 1/2 of 4 times 12 times the sine of 81 degrees. And that's just a calculator problem. So 24 sine 81 degrees. 23.7. That's in square centimeters. Just look ahead real quick. So I have a fair bit more to go. Okay. So problem 5. Find the exact value of the sine of 3 pi over 8. So let's start by just analyzing 3 pi over 8 for a second. So 3 pi over 8 is the same as 3 pi over 2 times 4, meaning it's 1/2 of 3 pi over 4. So we're going to use a half angle sign, or a half angle formula for sine. So the sine of 3 pi over 8 is plus or minus the square root of 1 minus cosine of 3 pi over 4 divided by 2. Next, let's take a look at 3 pi over 8 for a second. And 3 pi over 8, well, 3 over 8 is less than 1/2, which means that 3 pi over 8 is going to be in quadrant 1. Since 3 pi over 8 must be less than pi over 2. It's also greater than 0. And it's for that reason that I'm going to choose the positive sign out of that plus or minus option. So this thing ends up being equal to positive square root of 1 minus negative root 2 over 2. Since 3 pi over 4 is in quadrant 2, and cosine is negative there, all of that over 2. For simplification, I'm going to multiply by 2 over 2. So this becomes the square root of 2 minus a negative. So plus root 2 ends up there, all over 4. And then that simplifies one more time. So we the square root of 2 plus square root 2, all of that over 2. And that's our answer. Okay. Next, we've got the cosine of 2 theta is equal to cosine theta minus 1. So I'm going to start with an identity for cosine 2 theta. Namely, that's 2 cosine squared theta minus 1. And that's equal to cosine theta minus 1. If I then add stuff over to the other side, 2 cosine squared theta minus cosine theta equals 0. Since if I add 1 to both sides, those would just reduce with each other. So then I've got cosine theta times 2 cosine theta minus 1 equals 0. I then end up with cosine theta equals 0, or 2 cosine theta minus 1 equals 0. And I'll end up with a few angles. Over here, from cosine theta equals 0, I get either pi over 2 or 3 pi over 2. On the right side, if I have 2 cosine theta minus 1 equals 0, this means that cosine theta equals 1/2. So my angles then are pi over 3 and 5 pi over 3. So I'll just have to put all of those in the box. Pi over 3, pi over 2, 3 pi over 2, 5 pi over 3. Actually, you know what? Let's arrange them like as if they were in quadrants. There we go. That just makes it look a little nicer. Yes, that is correct. Cosine 2 theta is equal to 2 cosine squared minus 1. Yep, it's a double angle formula. Okay. Problem 7, tangents equal to a thing. Show all work including a reference triangle. So over here, we can see that U is in quadrant 2. But if we multiply that by 1/2, we get that u over 2 is in between pi over 4 and pi over 2. Which means that the angle u over 2 is located in quadrant 1. So we'll need to use both of those quadrants to solve this thing. So starting with a reference triangle for u, I'm going to put it in the second quadrant because that's where u is. This is angle u. And tangent u is negative root 39 over 5, so that's opposite over adjacent. Root 39 here, 5 goes there, and we're in the second quadrant, so the negative should be on the adjacent side. Then we'll need to get the hypotenuse. C squared is 5 squared plus 39. So 25 plus 39 is 8, or is 64. So C is going to be 8. So the half angle formula for cosine is plus or minus the square root of 1 plus the cosine of u divided by 2. But keep in mind that I'm looking for the cosine of u over 2, which means if I'm deciding between the plus or minus on the outside of that square root, the quadrant that's important is the quadrant of u over 2, which was quadrant 1. So the cosine of u over 2 is positive, while the cosine of u is negative. Because, again, u is in quadrant 2, but u over 2 is in quadrant 1. So now we just have to plug some stuff in. This is equal to positive square root of 1 plus negative 5 over 8 over 2. So then this is the square root of 8 minus 5 over 16. So root 3 over 4. Yeah, looks like that'll do. Okay. And then now we have this problem. So I have a tangent difference problem where on the inside of that I have the sine inverse of negative 11 over 61. Cool. So what this means is that if I go to the tangent difference formula, I should find that it is the tangent of theta minus the tangent of pi over 4 divided by 1 plus tangent theta tangent pi over 4. Where I already know what the tangent of pi over 4 is because it's off the unit circle, but I'm going to need a reference triangle to get uh, the tangent of theta, since that is really just, it's the tangent of the sine inverse of a negative 11 over 61, but writing all of that out is cumbersome. So we just are going to make a substitution. So I have the sine inverse of a negative number, which means I'm into the fourth quadrant. And we'll pretend like that's drawn to scale. Opposite over hypotenuse, so 61 goes there, negative 11 goes here. I'll use the Pythagorean theorem to get that this side is 60. Let's also label theta. It's that little guy right there. So if I go back up to that formula that we're going to use, I'm going to have one number minus another number divided by 1 plus a couple numbers multiplied together. So the tangent of theta should be opposite over adjacent. So negative 11 over 60. Tangent of pi over 4 is 1. So I can plug both of those in. And this is still negative 11 over 60. So now we just want to simplify this mess so that I don't have fractions within fractions. I'm going to multiply 60 to both top and bottom. Doing so gets me negative 11 minus 60 divided by 60 minus 11. And then that can all simplify. I've got negative 71 divided by 49. All right. And that's it.